Hello all, welcome to our final project presentation for ECE695. So we studied the Elastic Cache implementation for modern GPU architectures and compared its performance with sector cache implementation. And we also studied if we lock down certain addresses inside L2, how does it affect the performance of the GPU. We know that L1 caches inside GPU cores are smaller in size, and as the cores are empty by nature, makes the L1 cache more thrash prone. And if the benchmarks that we are running or the application that we are running are have divergent memory access patterns or irregular memory access patterns, like for benchmarks like BFS and NW, they generally don't benefit much from L1 cache. So even if the L1 cache is sectored like in Volta. So what the Elastic Cache says is that it introduces something called as chunk tags and common tags, and the combination of them actually helps us to manage both 128-byte access and 32-byte access, and helps us store both continuous sectors and non-continuous sectors in the same cache line, hence the name Elastic. So if we have 32-bit address, we keep the uppermost 6-bit as common tag, and we create a chunk tag out of those address. We take the lower 14 bits of the 20-bit tag and 2 upper bits of the 7-bit byte index, because it's 120-byte cache line, and we create a 16-bit chunk tag. We can see in a single cache line we have 4 sectors, and each sectors have an associated chunk tag with them and a single common tag with them. And storing different chunk tags, storing individual chunk tags for individual sector in a line, helps us store non-continuous sectors inside a single cache line whenever necessary. So whenever an access comes in, it first checks the common tag, and if it matches, then only it will look into corresponding chunk tags for corresponding sectors and result in hit, miss, or word miss. So this is our unified L1D shared memory as we know. So we added our common tag and chunk tag array inside the tag unit like this. So one of the papers says that we can add the chunk tag array inside the unused portion of the shared memory, but we don't want to do that for the modern GPU architectures, because in architectures like Volta, Turing, and everything, they have adaptive cache configuration where they transfer unused portion of the unused shared memory to the L1 cache. We don't want to hinder that optimization. That's why we added a separate chunk tag array. And area and power can be optimized, but I don't want to go into details of the physical design here. So this is the flow chart which goes through what happens when a tag during a tag lookup. But I think it will be better explained. It can be better explained with the help of following diagrams. So for hit, first common tag will be looked up, and it will definitely, if it matches, then good. Then the chunk tag will be looked up. Now let's say the sector ID of the requested address is 2. So first of all, it will look into chunk 2. If it matches there, then good. For this example, it does not match. So if it does not match, then it will look into the next chunk, which is chunk 3. If it matches there, then it's good. For this example, it matches, so it's a hit. For simple line miss, which is analogous to normal cache or sector cache, there is a common tag mismatch. The common tag only does not match, and that's why it's a miss. We have to evict a line if necessary. Now comes a word miss, which is kind of slightly different from sector cache. In sector cache, whenever there is a sector miss, we evict an entire line, but in Elastic Cache, we will evict if necessary, we will only evict a single 32-byte sector. For differentiation purpose, we are naming this type of miss as word miss. So whenever an access comes, common tag matches. If you are taking the same example, the first chunk 2 will be looked up for match or a hit or miss. It misses in chunk 2. It looks into the next chunk, which is chunk 3. It misses there. It rolls back to chunk 0. It rolls back, misses there. It goes to chunk 1. It also misses there. So it becomes a word miss. Now we might have to evict a 32-byte sector if all of them are full using a LRU replacement policy. But let's take an example where chunk 2 and chunk 3 are full for a chunk 2 access, and chunk 0 and chunk 1 are empty. So whenever we are fetching a data from the lower level memory, we will fill it up in chunk 0, because chunk 0 is the lowest available chunk that is empty inside for that cache line. That's why even though the access is for chunk 2, the fetched data will come inside chunk 0. So that's the novel feature inside elastic cache which is different from sector cache, and this feature works perfectly fine for continuous sectors and non-continuous sectors also. We have also extended the elastic cache implementation for L2 also, just to see how it performs with respect to sector cache. We can see when just L1 is elastic, then irregular memory applications like NW and BFS outperform sector cache, and other regular memory access patterns does not degrade much. Whereas when both L1 and L2 are elastic, then we see that it becomes detrimental to the detrimental for the performance. We also vary the associativity of L1 cache just to record the performance, and we see that NW's performance degrades for reduced associativity, whereas BFS improves. The good thing is that for many regular memory access pattern benchmarks also, with reduced associativity, elastic cache, L1 elastic cache outperforms sector cache. So this is a key point that we might want to keep in our mind while designing future architectures in order to extract maximum performance gain. We also measured performance of L1 elastic cache for Volta and Pascal architecture. We saw that Volta outperforms L1 elastic cache in Volta outperforms performance gain in Pascal, mainly because in Pascal L1 cache size is larger than Volta, so which is kind of intuitive that elastic cache performance will be better when our L1 cache size is smaller. The next part of the presentation will be taken care by my project partner Vivek, so I will hand it over to him. So thank you from my side. Bye.
We plot the miss rate of sectored L1 versus L1 elastic cache for different associativities. We see that benchmarks showing IPC improvement see an improvement in the miss rate as well. Irregular benchmarks show the best possible performance. Regular benchmarks do not show performance improvement or degradation, and this is expected. For experimental purposes, we made L2 cache as elastic, but we did not see any additional gain. We see that changing the associativity benefits a certain type of applications when running in L1 elastic cache configuration. For smaller sized L1, elastic caches perform better. We move on to the next project where we did a performance analysis of locking down certain addresses in the L2 cache in Volta. For locking down addresses in the L2, we followed 4 different algorithms. In the first algorithm, we run the benchmarks in profiling mode. We construct a profile file which consists of list of addresses that go to L2 along with their access count. Next, we run the benchmarks in lockdown mode. During eviction, if an address inside the profile file becomes the eviction candidate, we don't evict it. Instead, we evict the way which is the next best. If all the ways in the set are locked, then we bypass the access directly to DRAM. In the second implementation, we do not maintain a static profile file. Instead, we construct the locked list in flight. In the third algorithm, the profiling of addresses is similar to implementation 2, but we reduce the access count of addresses which go above a certain threshold. In this way, if an address gets into the locked list and never gets access for a very long time, its access count gets reduced by 1 every cycle. After some point of time, it goes below a certain threshold and becomes an eviction candidate again. In all the 3 algorithms, if all the ways in the set are locked, we bypass the access to DRAM. In relaxed locking, we do not do that. Instead, we evict the way with the least access count. We plotted the performance of sectored L2 versus L2 lockdown in the first 3 implementations versus the L2 relaxed lockdown. We do not see any performance improvement except in Needleman bunch. This is because L2 caches in Volta are larger in size with higher associativity. Hence, we conclude that L2 locking is not a good optimization for recent architectures as it just introduces additional area overhead. As part of future work, we can optimize the implementations that we did for L1 and L2 in elastic cache configuration. Using compiler support, depending on the type of application that we run on the GPU, we can dynamically change the associativity for L1 cache. To effectively implement L2 in elastic cache configuration, we can also study the changes in memory controller that needs to be done. This concludes our presentation. Thank you.